Prime factorization, I want to show you some things on paper. You've probably seen this before. We're, we're going to talk about in these lessons, and this will be a separate video because it's good to look at. But basically making a factoring tree, it isn't shown in this book. But if I have a number like 12, and I want to prime factor that, well, first of all, prime number is a number that has only two factors. Remember, factors are parts of a multiplication. So I can break this down into a multiplication, and then I'm done if I get to a number that only has two factors, and that would be 1 in itself. And that is the definition of prime. It means that it has exactly two factors. Well, 12 is not prime. You know, if I listed factors of 12, I'd get like 1 times 12, there's 2 factors. 2 times 6, there's 2 more factors. 3 times 4. So there's actually 6 factors of 12. This is called a composite number. Well, doing factoring trees is a nice organizational method to prime factor. And so what I'm going to break 12 down into basically lines of multiplication that will equal 12. So I might know that 3 goes into 12, and I take 3 times 4. So if I multiplied across 3 times 4, I'd get 12. And then I check and I say, well, is 3 prime? What that means again is that there's only two factors of 3. Well, and that's true. There's only 1 in itself. 1 and 3 are the only factors of 3. That makes two factors. That is a prime number. Then I look at 4, and there's actually 1 and 4, and then 2 times 2. So there's actually three factors. If I list the factors of 4, I'd get 1, 2, and 4. Well, then that's not prime, so I want to tree that into another multiplication, which would be 2 times 2. Is 2 prime? Yes, it is. It's got two factors. Okay. Well, what this leaves you with is a prime factorization of the number 12. In other words, if I multiply 3 times 2 times 2, I get 12. And for every number, there is a unique, there's only one prime factorization for every number. So what this is another way to represent 12 as a multiplication. So these factors. Now this is going to become real handy when we're talking about fractions. And I'm going to come back to this a lot of times in our book material. So hopefully you're real clear on this is a memorized method to get this, but I really want to emphasize, what does this mean? This is a prime factorization. So if I wanted the right prime factorization of 12, I'd go 2 times 2 times 3. We usually do it in ascending order. Well, let's do another one. Let's say like 28. Well, I could start anywhere. And the other thing too is that these trees could look differently and get to the same prime factorization. You know, with 12, actually let's do 12 again. I'm going to change that to 12. And this time I remember, or I think, well, 2 times 6 is 12, right? So I could put that there as long as those multiply to be equal to 12, which they do, I'm good. Well, 2 is prime, so I'm done. I'm going to leave that there. And then 6 is not. It has 4 factors, 1, 2, 3, and 6. So that is not a prime number. So I'm going to split that into 2 times 3. And look, I get exactly the same prime factorization, even if I do the process in a different order. Well, let's do another one like 28. I might see that 7 goes into 28. And that would be 7 times 4. And then I check to see if they're prime. Is 7 prime? Yes, it is. There's only 2 factors. And 4 is not. There's actually 3 again. So I can factor that down into the prime numbers of 2 and 2. So the prime factorization for 28 is 2 times 2 times 7. Okay? So this is a very good method to do prime factorization. And I hope that you get real comfortable with doing this, because it's going to be very handy, especially when we start factoring fractions, and we're going to factor a lot of things in this class. And the best way to make sure you never miss a common factor is to prime factor everything. So then I can say, well, what is common between these two things? And I get this idea here. Well, I got 2, 2, and 3 are my prime factors. Here I got 2, 2, and 7. They have a 2 and a 2 common. And one way to organize this could be like a Venn diagram. I could put these circles here. And let's say this number here is 12. And what this circle represents is all the prime factors of 12. And then I'm going to make this circle on the bottom circle here represent all the prime factors of 28. Well, when I look at these things, this overlap of the two circles would be where I have the same numbers, right? In other words, they overlap on these 2 and 2, right? So I've used up a 2, and if I look in this circle, I got a 2 and a 2. Well, this circle represents all the prime factors. I already got a 2 and a 2 in there, but I need a 3. So I still have a 3 here. Well, now let's look at the circle 28. Well, 28 already has a 2 and a 2, these two prime factors here. And what's left that's not represented in the circle is 7. So what I have here, again, if I cover up this part right here, there's all the prime factors of 12. If you multiply 2 times 2 times 3, you're going to get 12. If I cover up this portion, here's all the prime factors of 28. 2 times 2 times 7. And why this is a very nice tool to organize some things is this represents my common factors very well. I have really 4 as a common factor between these two. So if I had a fraction of 12 over 28, when we prime or when we simplify or take a fraction to its simplest form, it's called. Well, the definition of a simplest form is that there are no common factors between the numerator and the denominator other than 1. Well, we've already determined that there are 2 common factors here of a 2 of each, right? And really what we're doing is, what I can do is reorder this. I could say, and here's a real key important part about fractions that I'll come back to, is really I can represent 12 as 2 times 2 times 3. I could represent 28 as 2 times 2 times 7. And what I can do, because of the way fraction multiplication works, I could break these into separate fractions. This is really 2 over 2 times 2 over 2 times 3 over 7. Now why do I do that? Is because 2 over 2 is equal to 1. Or if I have the same numerator and the same denominator, that fraction is equal to 1. So what I've done is broke these into fractions equal to 1, and then what's left is this 3/7. This is why I can prove that 3/7 is the same value or the same position on a number line as 12 over 28. In other words, 1 times 1, and we'll talk about the identity property for multiplication too, times 3/7 is really 3 over 7. I think I went off the screen there. Okay, so 3/7 there. Okay? Still kind of there. Well, back at this Venn diagram again. If I put a line through there, what do I have? The fraction 3/7. This is a very nice tool to simplify fractions. The other thing too that I'll just talk about a little bit, and then I'm going to draw some more pictures, but this diagram, I could say, well, you know, it really is important to understand this portion rather than some fancy tool using Venn diagramming or anything else. what's really important in simplifying fractions is that we understand that really what I'm doing is reordering. I can change the order. I can break it down into a multiplication of prime numbers. Then I can reorder it in any order I want because it's multiplication. And I can make these common factors sit over each other and basically make fractions equal to 1 and end up with whatever's left over will be in simplest form, because what are the common factors between 3 and 7? 1. That's the only common factor, because 3 is 1 times 3 and 7 is 1 times 7. The only common factor between those two is 1. Then I know that this fraction is in simplest form. That's the definition of simplest form. And I'll just say a little thing about this. If I was looking for the LCM, the least common multiple, between 28 and 12, I can do this same diagram, and then I multiply what I see in the circles. In other words, this manages the common factors. And if I think about that, well, I don't have to get real fancy and say 3 times 2 times 2 times 7, and I could do that, but I already know what this multiplication is right here. This circle right here is equal to 28. So what do I do to get the LCM? Is I take 28 times what's not in that circle, which is 3. And then I'll get 60 plus 24, 84. Okay? So let's go back, and I'm going to do another video. I'm going to stop there just kind of talking about prime factorization and simplifying fractions. And then I'm going to come back to finding at least common multiple using the same method of prime factorization, because we're going to use this a lot. And where we use a lot of LCMs is when I add fractions, I have to have the same denominator, the same size piece, to add fractions. But I'll stop here and I'll make another video on that.